Welcome to this lecture in the PHAY0033 series, Formulation of Small Molecules. Today we're going to talk about dry powder inhalers, which are a very specific type of drug delivery system. So what are the learning outcomes from today's lecture? Well, by the end of the lecture, you should be able to describe the challenges of the pulmonary route, that is, getting drugs into the lung. You should be able to know the types of inhalers that are available and explain how they operate. The most important one, and the one that we're going to focus on, is dry powder inhalers. So by the end of the lecture, you should be able to explain in some detail how dry powder inhalers are formulated. Within that, you need to understand the role of surface energy, because it's very important in defining how dry powder inhalers operate. And you also need to understand how the physical form of the actives and the excipients impact the performance of dry powder inhalers. So, if you're okay with that, grab yourself a cup of coffee. If you haven't got one already, then I suggest you pause the video, go make one, and let's make a start. So let's first consider pulmonary delivery. Pulmonary means to the lung, and it's a very common route of delivery, second only to oral delivery. There are many reasons why this is the case. One is patient compliance. Clearly, most patients prefer taking tablets and capsules, but many patients are also happy to take drugs from an inhaler, so it's a very popular route of delivery from a patient perspective. Secondly, the lung physiology means it has a huge surface area, because it's designed to absorb gases from the surroundings. We can exploit that for drug delivery, because if we're not trying to treat something inherent in the lung and we want to get the drug systemically, there's a huge surface area for drug absorption to occur. And the third reason it's very good is because if you think about absorption from the gut, when the drug passes into the bloodstream, the first place it ends up is the liver. The liver's role is to remove things that it considers harmful and toxic. And quite often the liver thinks drugs are both of those things. So we can lose quite a lot of drugs through the liver. But when we give the drug via the lung, we don't have first pass metabolism. And so we should get higher systemic concentration of drugs. Is it an easy route of delivery? The answer is no. If you need convincing of that, think about how many tablets and capsules are on the market relative to how many inhaler products. Not many, right? One of the reasons for that is because it's a really difficult challenge to get drug particles into the lung, as we shall look at later. We have to design very specific devices in order to achieve that, and it's not easy. Secondly, even though as scientists we design these devices, patients might not use them properly. So it's as important that a patient is trained how to use an inhaler as it is how the inhaler itself is designed. Generally, we don't have to tell a patient how to swallow a tablet, for instance. Another problem is that you might be surprised when you hear how much drug is actually delivered to the lung from a commercial inhaler. You might think 90 to 100% of the dose is delivered, but in reality, you'd be lucky to get somewhere between 20 and 25%, and it can often drop as low as 5%, and that's for a commercially available product. We're going to look at some reasons why that is the case later on. And the last one is that if you think about asbestos and lung cancer, for instance, there's not a lot of evidence as to what the long-term exposure to the lung of various compounds is. And so it's very unclear what formulation ingredients you can use and what the consequences are for patient health for constantly breathing things into their lungs. Okay, the lung is designed for gas exchange, not really for particles. And so as a consequence of that, there are very few excipients that can be used for inhaler formulations. So one common theme of inhalers is that they all generate an aerosol. And an aerosol is simply a cloud of something which can be breathed in. That something can either be liquid droplets or it can be solid particles. Okay. The size of those droplets, it doesn't matter whether it's a liquid or a solid, is absolutely critical in getting those particles into the lung. So on the screen in front of you is a diagram of the lung, and you can see that the airway comes in and it branches, and those branches keep on going until we get down to the alveoli. Now, if we want to get particles actually to enter the lung, we have to make them very small. If we make them large, when the patient breathes in from the device, those particles just impact the back of the throat and then they are swallowed. So they end up in the stomach as if it was oral drug delivery and not into the lung. If you think about the airways going into the lung, there's lots of curves and bends, and we need the particles to be able to follow those bends. If the particles are too large, as the air goes around a corner, the particle just carries on and it impacts the surface of the lung. Okay? So what that means is we have to get the particle size down under 7 microns if we're going to target the lung in any shape or form. You might not have a feeling for how small 7 microns actually is, but it's an extremely small particle, and it has some consequences for how those powders behave, which we'll look at later on. But if we do get the particles down to between 2 and 7 microns, then generally when a patient breathes those in, they will get into the alveoli of the lung. If we want to target the really small sections of the lung, we need to get a particle size down to 0.5 to 2 microns. But generally, for a commercial product, the particle size distribution in the powder is going to be somewhere between 2 and 7 microns. I should say, because you might ask, why don't we just make the particles even smaller? If large particles are a problem and they impact the back of the throat when you breathe them in, why not make the particles really small? And it's a good question. And the answer is because if you make the particles too small, what will happen is they just remain suspended in air. So a patient would breathe that in, the particles would get into the lung, but they remain suspended in the air while they're in the lung. And then when the patient breathes out, they exhale those particles again. So small particles will go in and come out. Large particles are going to impact the back of the throat, and there's a very narrow window in which we need our particles to be in order to get good delivery to the lung. Now we're going to look at some of the devices that are used to deliver aerosols before we consider dry powder inhaler formulation. And you may have heard of some of these delivery types. There are only 3. The first one is a nebulizer. I'm going to mention it and we're not really going to look at it again, at least I'm not in this lecture, because a nebulizer is delivering a liquid particle. So the way that would work is you have your drug in suspension or solution, and the nebulizer itself is creating an aerosol. There are a number of ways in which an aerosol can be created, but one of the really common ways is a vibrating mesh. So you just have a mesh, it vibrates really fast, and that generates a cloud of droplets that the patient breathes in. I'm sure you're familiar with nebulizers, but they're designed to operate continuously. So they're often connected to a mouth and nose piece that would be put on the patient's face, and so that patient is constantly breathing in that aerosol. And it's a slightly different type of delivery from that which we want to focus on today. The second one on the screen in front of you is a more common type of inhaler, one you've probably either used or seen someone use. It's called a pressurized metered dose inhaler, or PMDI. Okay. Now they were very common types of inhalers, and the way they work is you have your drug suspended either as a suspension or a solution in a propellant gas in a canister. So the metal canister in that device is what's containing the product. Okay. The way that it works is when the patient needs to inhale, they push down on the canister, and the pressurized gas inside, some of it is released through a metering valve into a small chamber. Then the patient breathes in, and the aerosol which is generated gets into their lung. It's really important to recognise with this type of device that the patient has to coordinate their breathing with the action of the inhaler, because it's the inhaler itself which is generating the aerosol because of the compressed gas within it. So what that would mean is the patient has to take the aerosol, they have to be ready to breathe in, but then they need to push down on the device to create the aerosol and then breathe in afterwards. So push and then breathe in. If the patient miscoordinates that, so let's say they activate the device and then breathe out, they will then blow the aerosol away and they'll get no drug into their lung in the first place. So one issue with PMDIs is that the patient has to coordinate breathing with actuation. On the other hand, that is actually a benefit for PMDIs if you're trying to treat a lung condition, let's say someone's having an asthma attack, they don't have very good lung function in the first place. So the fact that the device is generating the aerosol is actually a good thing. It means they don't have to try and breathe really hard to get the device to operate. The device is doing it for them, but they do have to coordinate their breathing with actuation, and it's really common that patients miscoordinate. So it requires quite a lot of training on the part of the pharmacist when the device is given out. Another problem with PMDIs, and you may be familiar with this from the news, is that they used to contain compounds called chlorofluorocarbons, or CFCs. CFCs are really good propellants, and they're really good for suspending or dissolving drugs. But when they're released into the atmosphere, they react with ozone and they create a big hole in the ozone layer. So as a consequence, they were banned. So what that meant is most PMDIs had to be reformulated with a new range of propellants called HFCs, or hydroxyfluorocarbons. Now originally, HFCs were considered to be safe, but recently they have also been discovered to be rather bad for the ozone layer, and so they are about to be phased out as well. And so the hunt is on for a new class of propellants that can both suspend or solubilize drug and generate an aerosol when the device is used. But right now the risk is that PMDIs are going to be difficult to formulate. So there are a number of problems with PMDIs, and the main advantage is that the patient doesn't have to generate an aerosol with their own breathing. So that leads us to dry powder inhalers. They look rather similar to PMDIs, but they operate on a completely different principle. In this case, the device itself contains the powder. We're going to look at the powder formulation a little bit later. And when the patient needs to use it, that powder is dispensed into a small chamber, and then the patient breathes in. Now, in this instance, as the patient breathes in, the turbulence in the airflow caused by them inhaling lifts the powder particles from the device and should carry them into the lung. So unlike a PMDI, in a dry powder inhaler, it's a breath-actuated device. It's the inhalation effort by the patient which is aerosolizing the powder and causing the drug to get into the lung. What that means is there's no need for a propellant or any sort of metering device, so that makes the device a lot simpler. The downside is that the patient has to be able to generate enough aerosol force to generate this aerosol in the first place, and if they don't, they won't aerosolize the powder particles properly. Now, if you're following what I'm saying, that can be a bit of a problem if we're trying to target something where the lung itself is impaired, such as an asthma attack. You can be in the middle of an asthma attack, you don't really have a very strong breathing effort in the first place, and therefore to try and generate an aerosol when you can't breathe properly is rather difficult. And so for acute systems, PMDIs are preferred. But where we're trying to treat something which is less chronic, or the patient has good breathing capacity, or maybe we're trying to treat something systemically, so there isn't an issue with the lung in the first place, dry powder inhalers are the way forward. They're solvent-free, they're often excipient-free actually, and the patient cannot miscoordinate breathing with action because they have to generate the aerosol themselves as they breathe in. All of this means that dry powder inhalers are the preferred type of inhaler for most delivery systems. For one thing, the formulation itself is just a dry powder. Now if you think about tablet compaction, obviously that involves a tablet press, but what's going into that tablet press is a dry powder, and therefore the pharmaceutical industry is very well set up both for designing and handling dry powders. And so that's a very familiar thing for pharmaceutical scientists, to take a powder which is going to go into a tablet and then change it to go into a dry powder inhaler. The other reason they're so popular, and I said it just now, is because they're breath actuated. It's not possible for the patient to miscoordinate breathing with action. It is possible for a patient not to breathe in hard enough so they don't actually generate an aerosol, but they can't miscoordinate breathing with aerosol generation. So how do we formulate dry powder inhalers? Is it just a simple matter that we get our drug particles, make them 5 microns or thereabouts, and stick them into the device? Absolutely not. There are a number of reasons why this is a huge technical challenge. The first one is the size of those particles. I said already that 5 microns is a really small particle size, and it's really difficult to make powder particles with that size, which we're going to look at on the next slide. And another reason it's difficult is because the properties of powders change when they become so small. Generally, small powder particles are either adhesive or cohesive. Now we're going to look at those two terms later, but for now just remember adhesion means two different things sticking together. So one surface, different surface, and cohesion means two of the same things sticking together. Okay, so when a powder is very small particle size, it becomes very adhesive or cohesive, which means it either wants to stick to itself and form great big clumps, or it wants to stick to any surface which is around it. In particular, glass is a really good surface for adhesion. So they can be very difficult to process in a factory because essentially they're either sticking to themselves or sticking to something else. So the first thing to think about is how do we actually get powder particles with 5 micron diameter in the first place? I said already it's not an easy challenge, and there are only two options that you can do. You either start with molecules of drug in solution and try and crystallize them. That means the crystals are getting bigger and bigger as you stir them, and you stop the crystallization process when the particles are at 5 microns. The other option is that you crystallize normally and have big crystals, and then you reduce them in size to 5 microns. Of those two, generally particle size reduction is the method that is used because it's a lot easier to let crystallization happen and get a whole range of different crystal sizes and then reduce those crystal sizes in some way to a constant size than it is to control the crystallization process going up. Okay, so what that means is the pharmaceutical industry has a number of ingenious ways of reducing the particle size to get down to this 5 micron level. So we'll have a look at some of those processes. The main one is milling. So milling is a sort of high energy process. Essentially you're smashing the crystals in some way in order to reduce their particle size. There are two really common types of mill that you'll come across in the pharmaceutical industry, and we're going to look at both. One is an air jet mill and one is a ball mill. On the screen in front of you is a picture of an air jet mill, and it's an incredibly simple piece of kit. The way it works is it simply uses a high pressure airstream to spin the particles around, and the particles are spun in such a way as they hit each other. Okay. So on the left hand side of that picture you can see a thing that says feed funnel. You put your crystals in there, large crystals, and they go into a chamber in the centre where they're spun around in this air. The powder particles then hit themselves, and every time powder particles hit, energy is released and it causes the powder particles to fracture. As they fracture, they get smaller in size. The really clever thing about an air jet mill is it's set up so that as the particles get smaller and smaller, they will move towards the centre of the circulating air. Remember that larger particles under centrifugal force tend to go to the outside. So what that means is smaller particles tend to move to the inside. And if you look at the picture, you can see that the exit from the air jet mill is in the centre. So in that sense, it's kind of self-regulating. The airflow is set up so that a powder particle only gets to the centre of the air jet mill when it's below 5 microns. So it can't actually physically be ejected from the mill until it's got down to 5 microns. So you can put any size powder particles into the air jet mill in the first place, and they will stay there long enough that the particles get down to 5 microns before they can exit. Other than that, there's solvent free. It's a very simple system to use, and it can run continuously as well. If you think about it, powder can constantly be put into the funnel on the left, and it's constantly removed from the hole in the centre of the mill. So it's a really good, cheap technique. Very few moving parts. It's just using air to break the particles down. The other type of mill is a ball mill. And so, as the name implies, it uses balls, ball bearings in this case, stainless steel ball bearings, to smash powder particles to a smaller size. Think of it like pulverization. So we have one of these in the school actually. You might end up using it during your project later in the year. The way it works is you have a ceramic jar into which you put your powder and you put some ball bearings. In our case, the ball mill has 4 of these jars, so you put the 4 jars into the mill, you clamp them down, and then the mill starts to rotate. It rotates with a dual action. So what that means is all 4 of the jars go round in a circle, and at the same time each individual jar is also spinning. So you can imagine that the jar is spinning and then the whole thing itself is going around in a circle. So it's a dual action. And the consequence of that is that the balls spin around on the inside of that jar, and every time they come into contact with the powder they apply an energy and it smashes the particle into a smaller size. Okay, so two different types of milling: air jet milling and ball milling. I'm sure there are other ways of reducing particle size, but these are the two most common that are used in the pharmaceutical industry. Now we have to be really careful when we mill something, because we have to understand what the consequence of milling is for the physical form of the powder. Remember that most powders start as crystalline materials, so what you're putting into the mill is a crystalline material. Some people, when they do milling, are only focused on particle size reduction. So when they take the powder out of the mill at the end, they look at it and they think, have I got the particle size distribution that I want? And that's all they think about. So many years ago I went to a company that's going to remain nameless, but it made dry powder inhalers, and they had a big ball mill in their factory and it was running out of its useful life, so they replaced it with a new ball mill from a different manufacturer. They spent 6 months setting up the ball mill to get the particle size distribution the same as their old ball mill. But when they used it and they took the powder from their new ball mill and they tried to make a dry powder inhaler out of it, it didn't work properly and they couldn't understand why. And so they asked me to go and talk to them about what the reasons might be. And the reasons for it are actually shown on the screen in front of you. And it's that they hadn't considered that by milling the material, they were also potentially changing the physical form of that material. Now, what do I mean by that? So one thing I mean by that is physical form. You should remember from earlier lectures, materials can be either crystalline or amorphous. If they're crystalline, they can be polymorphic, and we're going to finish this lecture with an example of polymorphism in dry powder inhalers, or they can be amorphous when the molecules are randomly distributed. And it's really important that we understand what type of physical form we have in the powder in our own inhaler. So the screen in front of you has an example of what might happen in a ball mill or an air jet mill. You start with a crystalline powder, and crystalline on my diagram is shown as purple. So we start with a large powder particle on the left hand side, which is 100% crystalline. It goes into the mill and it is reduced in size. So one large particle comes out, in this case, as 5 small particles. No problem there. But you need to think to yourself, what has happened in the mill? The mill, and it doesn't matter if it's an air jet mill or a ball mill, is applying a force to the particle in order to shear it in half. So imagine that a force is being applied to the material all the time. To start with, you have a large crystalline particle, and as a force is applied to it, that particle can fracture. No problem. So we end up with 2 smaller particles, both of which are crystalline. But what will happen is, if you keep applying a force to a powder, it will reduce in particle size to start with, but there will become a point at which it can't reduce in size any further. It's called the brittle ductile transition point. And we don't really know where it's going to be for certain powders. So what that means is we put the powder into the mill in the first place and we reduce it in particle size, but we don't know how long to leave it in the mill. I said already that air jet mills are kind of useful because the particle is ejected when it gets to the right particle size. And so long as that brittle ductile transition is around about the same as the particle size you're trying to attain, then the particles coming out of an air jet mill shouldn't be super amorphous. But in a ball mill, we'll leave the jars spinning for a period of time until we're absolutely convinced that we've got the right particle size. So if you think about manufacturing and you want to get particle size of 5 microns, let's say, and you think, well, maybe if I leave the ball mill running for 30 minutes, most of my powder will be okay, therefore I'll leave it for 60 minutes and then all of the powder should be okay. Those powder particles are still having energy applied to them in the ball mill. And if they can't fracture, those powder particles have to take that energy and do something with it. If they don't do that, the temperature is going to rise enormously. In fact, it's possible to get powders to melt in a ball mill if you're not really taking care of what's going on. So you think you're a small particle and a force is being applied to you all the time, you have to dissipate that energy. And the question is, how does the particle dissipate that energy? And the way it does that is by moving molecules. So if the material is crystalline, all of the molecules at the surface are arranged in a repeating pattern. But as a force is applied to those molecules, that force is dissipated by moving some of the molecules out of the crystal structure. Okay? And so you start with something which is crystalline, molecules are aligned, and you end up with something random or amorphous because the molecules have been moved by the force that's being applied to it. I hope you can see that if you have a particle with molecules all the way through it, the molecules that are going to be most affected by force being applied are those molecules which are at the surface, because those are the ones that are directly in contact with whatever is applying the force. And so the consequence of that is that when you look at a powder particle that's come out of a ball mill in particular, the surface of those particles tends to be amorphous. How thick that amorphous layer is depends on how long the particles have been in the ball mill. Now, we've done lots of research at the school over the years into milling particles and measuring amorphous content. And I can tell you that typically when you mill a powder for dry powder inhaler formulations, when it comes out of the mill, it's probably got somewhere between 0.5% and 2% by mass amorphous content. So what that means is up to 98%, 98 to 99.5% of the particle is still crystalline. Maybe only 0.5% to 2% is amorphous. But it's really important that amorphous material is going to be at the surface of those powder particles because of the way they're being treated. So if you look at my diagram, blue represents amorphous material, and you can see that I've got crystalline powder particles with a corona or outside surface of amorphous material. I want you to see right now that they may only be 0.5% to 2% by mass amorphous, but the way those powders are going to behave is completely different from, say, a powder that we might make which is a mixture of amorphous and crystalline material. So the example on the right hand side of this screen shows you what happens if we try and make a powder which is, say, 1 or 2% amorphous. The way we do that is we mix crystalline powder particles with amorphous particles made by, say, spray drying. If we want to make a 1% reference material of amorphous content, we're going to mix 99 parts of crystalline material with 1 part of amorphous material. Or another way of thinking about that, assuming all the particles are the same size, 99 crystalline particles for every 1 amorphous particle. So the diagram on the right is meant to represent what happens when we try and make a material which is 1% amorphous. There'll be 1 amorphous particle and 99 crystalline particles. But I want you to see that when you mill something, the way that the powder particles are arranged is completely different. Crystalline core with an amorphous corona around the outside. Both of those powder particles, or the powders themselves I should say, are 1%, let's say, amorphous content. But where that amorphous content is completely different between a milled powder and one that we've made by mixing powders together. And this has a huge consequence later on for how we measure these things and also how dry powder inhalers actually work. Right, that's quite a lot of information. So I propose that we go and get a new cup of tea. I happen to have drunk mine, so I need a new one. And when we come back, I'll talk you through the formulation strategies for dry powder inhalers.